All right, today we're going to do something kind of wild. We're going to decode the entire physical world. I mean, everything. Your desk, the coffee you're drinking, the air, even you. It's all built from the same basic stuff, and we're about to learn its secret language. So let's just jump right in. I mean, really think about that. If you could zoom in way past what your eyes can see, past even the most powerful microscopes, what would you actually find at the bottom of it all? Well, that's exactly the journey we're going on right now. So, chemists have this one simple but really powerful word for all the stuff in the universe: matter. Super simple, right? If it takes up space and it has mass, it's matter. And chemistry, well, that's just the science of understanding all that stuff: what it is, how it behaves, and how it changes. So here's our game plan. We're going on what I like to call a cosmic zoom in. We're going to start with the big picture world, the things we can actually see and touch, and then we're going to dive down level by level until we get to the absolute heart of matter itself. Okay, so you've got this universe filled with a nearly infinite variety of stuff. Where do you even begin? Well, chemists do what we all do when we're faced with a big mess. They start sorting things into piles. The first big sort creates two main bins: pure substances and mixtures. A pure substance like, say, perfectly pure water is the same all the way through. Every single tiny particle is an H2O molecule. But a mixture, like the air in this room, is more like a party. You've got nitrogen, oxygen, and a bunch of other gases all just kind of hanging out in the same space, not really chemically connected. Now, let's grab that pure substances bin and sort it again. If you've got something you just can't break down into anything simpler, at least not with chemical tools, you've found an element. It's made of only one type of atom. But if you can break it down into simpler parts, then you've got a compound. That's where different elements have chemically locked together to become something new. And this, right here, is where chemistry starts to feel like actual magic. Check this out. You take sodium, which is this soft metal that literally explodes if it touches water. Then you take chlorine, a poisonous green gas. You combine them, and you get table salt. Sodium chloride, something totally harmless and delicious on French fries. The compound isn't just a mix of the two. It's a whole new thing with its own unique properties. Now, it's not just about what stuff is. It's also about how it changes. A physical change is just a change in appearance. Think about ice melting. It goes from solid to liquid, but it's still H2O. Its identity is the same. A chemical change, though, that's a whole different ballgame. That's when a new substance is actually formed. Like when an iron nail rusts, it's not just iron anymore. It's become a new compound called iron oxide. The original stuff is gone. Okay, we've got our big categories sorted. Time to crank up the cosmic zoom. We're going in deeper to the fundamental building block of every single element: the atom. The crazy part isn't just what an atom is, but how we figured it out. See, scientists used to think atoms were like tiny, solid billiard balls. But then this guy, Ernest Rutherford, shot tiny particles at a super thin sheet of gold foil, and most of them went straight through. It was a total shocker. It proved that atoms are almost entirely empty space, with nearly all their mass crushed into this impossibly tiny positive center called the nucleus. So what's in there? It turns out there are 3 key players in this atomic game. Jammed into that nucleus, you have the positively charged protons and the neutrons, which have no charge. Then, zipping around way on the outside, in that big empty space, are the tiny negatively charged electrons. And it's the classic attraction between the positive protons and negative electrons that holds the whole thing together. So what makes an atom of gold different from an atom of oxygen? It's ridiculously simple. It all comes down to one number: the atomic number. That's just the count of how many protons are in the nucleus. That's it. It's the element's unique ID, its fingerprint. If an atom has exactly 8 protons, it is oxygen, period. If it has 79, it's gold, every single time. But of course, chemistry has a little twist. While that proton number is locked in, the number of neutrons can actually change a bit. We call these different versions of an element isotopes. They're all still the same element, chemically speaking, because the proton count is the same. They just have slightly different weights because of those extra or missing neutrons. Okay, so we've got all these elements, each with its own ID number and its own personality. How on earth do you keep track of it all? Well, luckily for us, chemists have the ultimate cheat sheet. I am talking, of course, about the periodic table of elements. And trust me, it's not just some boring chart you had to memorize in school. It's a map. It's a masterpiece of organized information. It lays out every known element by its atomic number, and in doing so, it reveals these incredible hidden patterns in how they behave. Now, you can read it like a book, going across the rows, which are called periods, but the real secret, the magic of the table, is in the vertical columns. These are called groups. And here's the cool part. Elements in the same group act like family. They have really similar chemical properties. The table also gives us a quick visual guide. Metals over on the left, nonmetals on the upper right, and those weirdos with mixed properties, the metalloids running along the staircase in between.
All right, so we've met the cast of characters, the elements. Now let's figure out how to talk about the compounds they make when they get together. We need to learn the language for their recipes.
And that's exactly what a chemical formula is. Think of it as the recipe for one single molecule, just written in a super condensed shorthand. It tells you exactly which ingredients, which elements you need, and exactly how many atoms of each. Let's break down probably the most famous recipe on the planet, H2O. Okay, the letters are the ingredients. H for hydrogen, O for oxygen. That little number, the subscript, tells you the quantity. So the 2 after the H means you need 2 hydrogen atoms. The O doesn't have a number, which in chemistry just means 1. So H2O, 2 hydrogen atoms, 1 oxygen atom. That's it. Okay, so here's another key part of the game. When chemicals react, the atoms aren't always neutral. They can actually gain or lose some of those outer electrons. If an atom loses 1 or more electrons, it now has more positive protons than negative electrons, so it gets a positive charge. We call that a cation. And if it gains electrons, it gets a negative charge and becomes an anion. Generally speaking, metals love to lose electrons and become positive cations, while nonmetals tend to gain them and become negative anions. And what happens next? Well, it's that classic story, right? Opposites attract. That positive cation, like our old friend sodium, Na+, becomes powerfully attracted to a negative anion, like chloride, Cl-. They snap together, drawn by that charge difference, and form a perfectly neutral compound. In this case, NaCl. Good old table salt again. But this brings up a huge problem. How in the world do you actually count atoms? They're way too small. You can't just pick them up one by one. This is where a really weird sounding but super important idea comes in. The mole. Just think of it like a dozen. A dozen is always 12 of something, right? Well, a mole is always 6.022 times 10 to the 23rd of something. It is a ridiculously huge number, but it's the magic number that lets chemists count atoms just by weighing them out in the lab. And let's just zoom back out for a second. Think about the journey we just took. We went from everyday stuff you can see and touch, sorted it all out, and then dove all the way down into the atom itself. We met the elements on the periodic table and even started to learn their secret language, the language of chemical formulas. So, we know the building blocks and we know how to write the recipes. But that leads to the biggest question of all, doesn't it? How do you know what's going to happen when you actually mix the ingredients? How do chemists predict which recipe will make a life-saving drug and which one is going to, blow up the lab? That is all about chemical reactions, and it's the next step on our journey.